see, I also use the same teacher mode, so like everyone is getting. When you insert the file, will just come and sit here. You can even pull it down, up. You can provide place it anywhere here. The file will sit here if you insert it. You paste also, the page will be sitting here. Okay, you don't need to do any other thing. Just paste it and close it. It is automatic. Save. You can only access. I can go and correct. Nobody can access in your area. See, each student they have their own. This is Ivan. Then that's a Limri thing. Just click homework. I click 2 only. If you want, you can add section learn. In this case, here I will provide week 1, 2, 3 like that. Then and there, whenever you finish. See, Ivan also having Limri thing, also having, and then Tonka, all are having. You go to your own name, and then you will have only your name because I am the organizer. You can add all the names. So just click. You will get the homework. Click. Go here. Download your question. Write the answer in a paper. Work out the answer. Photo. Paste it. Or attach the file. Scan and attach the file. It takes half an hour only, but I'm giving you 1 week time. You can do it leisurely, right? Okay, let's move on. Done this part. What else? Okay, last class we just started with introduction, right? Now you understood what are all the topics we are covering under this syllabus. Now let me start with the first chapter. Slides open here. We stopped here somewhere, right? Yeah, we stopped somewhere here. External loads, the types of loads, right? Types of loads and the forces, right? We can basically classify them into 2 categories. What kind of loads acting on the member, and what are all the body forces and its responses, right? The whole story is behind these 2 factors. Number 1, what kind of load is acting on the structure, and what's the response of the body, reaction of the body, or what are the body forces generated due to this external loading. These are the things you are going to see today. One moment. Let me take this zoom view. I'm not getting this. I don't get any of this thing. What happened? Okay, you can see my cursor moving?
Yes.
Okay, thank you. Number 1 is external load. The external, in one word I can say for your understanding, point load and distributor load, right? The distributor load is like this. It is acting, number 1, both of them are acting on the surface, right? Both of them are acting on the surface, in contact with the surface, on the surface, and it is transferred to the sections of the body, right? And coming to this point, it is like an applied load which is applied at a point, a single point. If it is applied at a single point, it is called a point load. Example 1, when there is a bicycle parked, if you stop the bicycle and park it, the wheel is exerting a force on the ground. So at the point of the wheel which is acting at a point and exerting a load onto the ground is called a point load. Okay. A water tank in a building which is located at the corner of the building on top floor is the point load acting at that point. That is the most critical point of the structure. So one have to design it, all the beams and columns connected to this point, take it as a critical point and then design it. And then the type is a distributor load. Distributor load, all of you know that it is over the surface, right? Per unit area, per unit run we calculate. Okay, per unit run, per unit length. I will show the photographs now. Okay, I just copy. Yeah, see, this is the point load. It may be a water tank. It may be a big table or a chair that you in future are going to have it. All the Almira going to come here, and it may be duct, right? Providing duct and host all the air conditioner things. And see here, these are all the point load, and this is also surface load. The resultant will be acting at the middle. They will decide based on the resultant acting at the middle. And if you say this one, this is the slab onto the beam. You know, this is slab, this is beam, this is column, This is footing and below is the foundation, right? The point of slab acting on the beam, if you see, the type of load is a distributed one, right? The whole length is acting on the whole length of the beam, right? The two bodies are in contact, exerting a load over the length, right? Over the length on a small strip, just on top is a small strip only acting, but later on it is distributed based on the material property. It will get distributed. You will get a stress distribution accordingly, and also the concentrations, right? Right. We can say this is a point load, this is a distributor load, this is again a point load, column, point load only. Just at a point of some cross section, 20 meter square, 40 meter square, or 2 by 2 column, 3 by 3 column, something like that we say. This is again a point load, right? You must know the variation of this load and its distribution, right? So that is what given here. The resultant force, if it is like this, group of point loads, so the resultant load will be taken as the taken for design. In case of gravitation, this force called the weight of the body. No, I'm not here. One moment. Here. So the resultant force over the area due to a distributed load, the resultant acts through the centroid. Yeah. In this case, the diagram we assume to be, you would have studied in moment of inertia. We start with this distribution, then only we go for integration of this moment of area. You see here, this is the one by one. You have small arrows acting on it. These are all the force lines, right? The loads or the force acting on the body due to another load on it. It might be the next floor, or the self-weight of the slab itself, or by any other type of loading. But how do you calculate? By following the resultant, because they are all uniform, right? They are all uniform. The centroid and if the body is uniform, symmetric, the resultant is supposed to be acting at the middle, at the centroid of the body, right? I repeat, if the geometry is symmetric, what is symmetric? If you cut at any angle, it will leave two halves on both sides, equal halves. If you cut here, rectangle on both sides of same size. Cut here, also same. Like that, the symmetry is maintained. Then the resultant will be acting at the centroid of the geometric center of the member. What's the difference between centroid and center of gravity? Anybody? Centroid and center of gravity of a body, differences. You would have studied again in moment of inertia calculations. You must know this, then you will understand the variation. Oh, I am in the notepad mode, no tablet mode. Can I explain me the difference? Just say, I will correct you, don't worry. It does not mean that you should know. We will correct. I take the attendance. Group 24. 4 more missing. Any idea, please? What's the difference between centroid and center of gravity? See, the word itself is there. Please think. Late in the evening, you should be alert by answering. Come on. Simple question only. Please answer. If you know, don't keep quiet. Please answer. You are helping yourself and also your friends and me. I feel active.
Center is the center object.
Geometric center of the object, correct. Centroid, center of gravity.
Total weight at the center.
Louder, please.
The total weight at the center.
Yeah, correct. He has answered correctly, but in a different way. Weight is also a type of force. Resultant force. Resultant force. It may be weight, it may be external load, or any type. He's correct. Just the resultant of all this type of loading, which is passing through the centroid. Some object will pass through the centroid, some object it will be displaced. Then you have, as engineer, you have to bother what is the dislocation or what is the lever arm, what is the shift from original centroid to the new center of gravity due to change in geometry or change in location, or the object may be found in water. Even worse, when the object is on ground, you design. When the object, say, you design a submarine, you design a offshore structure, or underground structure, or what else? A gate, the underground structure, meaning under the sea, underwater structures. The behavior of the structure will be totally different. Automatically, the center of gravity will get shifted. At that point, you have to, as a designer, you have to find both the change in point, the change in center of gravity, the location, and also the forces. Okay. If it is straight, you just determine the normal force. If it is inclined, you have to determine both. Right. Now coming to the another type of force. I think you are clear with this. Resultant force. When it is acting UDL, you have to calculate by the length, right? If it is per running meter, I think I will explain this part later on, how you are calculating the load for UDL for a beam when we do the calculation. For now, understand, for this type of structure, it will be acting at the center. We quantify it later on, right? Next type. So far we are talking about the external load, superimposed load. Now coming to another type of load, which is, these are all the basic categories. And next chapters or following chapters, I think in the design chapter, I think I will give you the detailed types of loads that one have to consider in your design. But for now, the very basic thing are external load and the body force. Okay, a body force is developed when one body exerts a force on another body without direct physical contact between the bodies. See? Example, include the effects caused by Earth's gravitation or its electromagnetic field, right? If the body is in space, no weightless, right? All floating. If the body is on Earth, because it is subjected to a gravitational force, it has mg, right? It has a weight, right? Although body forces affect, if you are designing, when you design a structure on ground and you go to Genting Highland, your structure is on the Genting Highland, you really have to mind your pressure value. There is a difference between construction of buildings on the ground, on the earth, on the structures constructed at a very high height, very high altitude, like Genting Highland, Himalayas, Alps. You really have to consider the change in pressure. Then only you can design properly, because the gravity changes, value of gravity changes, right? Where else? Where we are? All the body forces, each of the particles composing the body, these forces are normally represented by single concentrated force acting on the body. Yeah, we can convert them into a single concentrated body if it is of uniform composition. A body, a structure which is all of wood, all of concrete, you can calculate. What if they are different types of, or two different materials, right? Both polymer and metals are used, or wood and PVCs are used. So if it is a mixed type, then it is a problem. We have to determine one by one. But if it is of uniform composition, you can easily determine by a resultant value. In this case of gravitation, the force is calculated, called weight of the body, and acts through the body's center of gravity. Yep. So naturally, you must find the center of gravity by following the centroid of the body if it is symmetric. If not, you have to account for the eccentricity effect. Right. I'm going to give you some examples to understand there are so many examples, but I don't want to show you. I'm sure you will get depressed when you see those videos. But I request you to go through on your free time structural failure in the globe. If you see so bad experience, shocking news for you, how a crane crash from a very high altitude, right? We are also having, right? We just had last month beside our university. What if a crane collapse in a building construction? What if a dam collapse? What if a structure collapse? What if a top floor collapse, foundation collapse? All these things are mainly due to improper design improper understanding, and then ignorance of certain important factors of design. Okay, now Professor Bhargavi has given us a video. Actually, I borrowed from him. This video will give you the types of failures. As engineers, you should know what are the types of failures, modes of failures, so that you can design accordingly. Let me play for a while, just 5 to 10 minutes, I think. Let me take that video first. Understand the type of failure so that you can design accordingly. What are the forces you have studied? Types of forces. Just recall while I pick the slide, the video for you. Can you tell me what are all the types of forces acting on the body? Any idea?
Gravitational force.
Louder, please.
Gravitational force.
What else? Structural. I mean, apart from this, what are the other forces that you studied before? Just recall what you studied before.
The live load, dead load.
Yeah, result in what? What else?
Normal forces.
Remember. Okay, I start. Remember the tension force, compression force, bending, and number, right? Trusses you. The member can be either compression load or load is the force, some called as force, isn't it? It's about tension. Let me play this video. You cannot listen to the. I cannot hear. Just stop me. One moment. Types of failures I'm going to give you. Right now, I tell you there are in the meeting also I discuss about this problem. We can. I don't know why this is coming out like this. I don't know. I have to. Moment. I cannot share. What do you call? Window. It is all coming out to be the screen. What happened? Let me join again. What's I request students, you please join the team I'm creating. All right. Sometimes I already have the files shared ready with me, easy for me to run the class. Don't do open any class yourself, please. I cannot share. Where is the voice? I see. Right. Sometimes I come across this problem. I create one, the students create another one. Okay, can you?
And in 1980, when we help in terms of remedying this. I graduated in 19.
Can you hear? Can you all hear?
Yes, yes.
Okay.
1981, and then before continuing to do further studies, something happened in North Sea, and a few things happened actually in the world around that time. 1976, when I was finishing my A level, DC-10 engine actually coming off from the engine, from the plane in Heathrow Airport. That's in 1976. And in 1980, offshore platform called Alexander Keelan, one of the legs, they have 5 legs. It is a floating platform. They have 5 legs, and one of the legs actually come off, and the platform just overturned. So from the report, it relates to the failure, the mechanical failure, and the material failure in that particular situation. Now, those actually interest me in trying to look more detail about materials behavior, materials capability, and hopefully we will be able to help in preventing such catastrophe from happening. And I compiled those few I call components or structural stress related failure, okay, as the start of this particular course, so that you will be able to relate when we talk about stresses, we talk about component behavior, we talk about component capability, and if you are and you have the knowledge in that particular field as an engineer, you should be able to help hopefully in preventing those. So those are the preamble to this particular course because they are stress related. Now the first one is this one, a common work, right? Engineering work. So what is this? It's a normal telescopic crane, right? Being used to lift heavy objects, move heavy objects, and it's being used in construction site. Every day, actually, you see this one, right? In the construction site. Now, you would have thought that this sort of thing will never fail materially, right? But it doesn't do that. Now, this is one of the pictures of the telescopic crane is actually fail in bending. Can you see that?
Yes.
Oh, it's not visible. So so it can fail, and it fail in bending. The reason is that the bending stress is high compared to the capability of the materials being used to work out. Most bending or most crane, actually they have the capacity being built, how many tons that it can carry and so on. But somehow or other, this particular mishap, this particular part of that crane is actually just bent, and it cannot sustain the load anymore. And yeah, somebody is responsible for this particular thing. Investigation was happening. I do not capture when. Right, this is the first one, bending failure. CLO3 is talking about bending. Now, hopefully you can relate when we talk about CLO3 in that particular situation to how can this be prevented as somebody practicing or engineering practice. How to determine the bending stress so that it won't, this mishap won't happen. The second one, you see what is this? Ship. It's quite a large ship, right? You never thought that the ship will crack in the middle there. Right? Now there's a crack right in the middle, and this particular ship, I think it's called it Infinity or something like that. You can check in the internet. By the look of the picture, is quite, I think in 1970s, I suppose, 60s, there's no color picture. And it cracked in the middle, and actually the two halves will just sunk in that particular year. Okay, this is one of the disasters, and there are actually being analyzed, and they look at how the load distribution at the top and also the buoyancy of this. They find that maximum bending moment occurring at that particular point, and this causes bending of the shape. A similar one happens there, right? This is barge being loaded with still in the wharf. Basically, the crane is loading and unloading, and you can see it actually break into two in the middle. Again, looking at the buoyancies, I think there's some analysis and so on. I think some papers being done, investigation, and it does actually have a high bending moment in the region where it cracked, right? So it is stress related. The material in that particular location, the stress is too high that the material cannot withstand that particular stress. It could be welding in there. It could be a continuous material, all sorts of things. But even a large piece of structure like that actually do fail when under stress or under external load. So these are buoyancy load, buoyancy supporting it, and there's a external mechanical load on top of this particular barge. So this is the one. This one happened during the time when I was doing a bachelor degree. Actually, must be 70s, 80s, because I remember this is one of the case that we actually I won't say discuss in detail, but it's taken as a catastrophic example of it's mechanical. It's related to mechanical thing. This one is quite later, not earlier, but later, because there's color photos. This is quite common. This is gear tooth. Okay, this is pitting. This is the tooth, and this is gear tooth. You can see the crack there. Yeah, this is caused by bending, actually. So you don't like this one when it happens in your car gearbox, right? So this happened because of the bending stress at the tooth root is too high. It's either the torque is high, sudden jerk in torque is being transmitted, and that can cause the tooth to break. So this is breaking due to high bending stress. Whereas on the left-hand side here, this is pitting of the surface of the gear tooth, actually. So it doesn't break, but there's a sign of shear failure because of the contact stress is very high, and it's caused shear as time goes. But this is certainly bending breakage. It is a break like that. It will fall off. Okay. Don't know why it hang. Okay. This is another example of gear tooth break. And this is break. It break due to bending. That means it has intermittent bending. It is being, we call it fatigue. In other words, the bending moment is cyclic. In other words, it is on, off, through a certain cycle. So at the end of the day, it will end up fatiguing, and these gears will lose tooth, basically. And if this happens, the only thing you can do actually is cannot be repaired, the whole gears to be replaced. And just imagine if this is happening when the vehicle is still on the road and still moving. And worse still, if it moves downhill or something like that. So lots of things may happen there. Okay, so this is bending brake and bending fatigue. So the word bending is there, and I would say all the three is talking about bending. So you should be able to relate that. This is crankshaft. Crankshaft, this is when it is good. That's what the shape look like. And crankshaft is actually transmitting power from the reciprocating piston through connecting rod, and then that power is transmitted on the left-hand side there to the wheel or the flywheel of the engine, and then the flywheel will actually connected to the clutch. Now, in this particular case, that portion that is transmitting the power actually failed. Now, this is brittle material. The surface on which it failed is about 45 degrees to the axis of this particular crankshaft, and it breaks like that. This is a break due to torsion, shear stress. Now, this is related to ClO2, talking about torsional stresses there. So these are the things that are directly related to this particular cause. And what we want to achieve is actually, how can this be prevented? How do we assess the limits of the sizes and the material to limit the torque transmitted so that it won't break like this? Okay, and it could be an expensive thing there. Right. The next one is also talking about torsional shaft. Now, this is if you have a rear wheel drive vehicle, like buses, lorries. So if you look underneath that vehicle, you can see this type of shaft. Yeah. So this is the engine is in front here, and then the gearbox, and then this shaft is rotating through this differential unit, and this differential unit actually rotate this gear, this wheel to propel the vehicle forward. Now this shaft is transmitting mechanical power, and it is under shear all the time. And if the shear stress is above the capacity of that, this is what will happen. Okay, this is the axis of the shaft, and this particular part is about 45 degrees. A typical brittle material failure and shear failure. Now the Mohr circle will tell us it is 45 degrees later on when you are on the Mohr circle. So by having the cause that we have, that you are going to, you are registering now, is to be able to predict what kind of failure it may get, and we'll be able to limit the value of the torque, the value of the external load, to prevent this from happening. So that's the importance of this. So shaft fails due to shear there. Now this is Alexander Keelan that I'm talking about. This is in North Sea, and North Sea is a very rough sea basically. If you learn geography, the North Sea is actually north of Scotland. The sea bit separating island Britain with the rest of the Europe, and this is how it is being designed. You have got a buoy at the bottom, a hollow spear that keeps this one afloat, right? And there are 5 of those. There are many designs. In this case, it is 5. And it is connected to this, what we call tubular joint. This is the leg, and this is the joint. This is K joint, basically. Okay, so it is not anchored to the bottom of the sea. So it's just floating like that. So the external forces will be the fluid forces or the buoyancy forces based on Archimedes principle, and sometimes you've got wave and then that one. So what happened in 1980 is that one of the leg, actually the holding of the leg here is actually break, and one of the leg come off of this particular structure. Now when it come off, this floating structure is supported only on 4 spears, and it gets off balance, and the whole thing will just topple and turn it upside down. So this is a similar construction. See, it's not yet. Can you see this one? Yeah, this is a weak point as far as this construction is concerned. So what happened in 1980? This is what happened. One of the leg actually break. It's not the leg, but the joint holding the leg actually break, and this part will become off balance because now the buoyancy actually is on one side and there is no opposite buoyancy. So everything just turn around, and what is supposed to be on top become the bottom inside the sea, and the legs is floating at the top. And this is one of the leg was pictured up that is come out. And this is how the view on the remaining 4 legs with the structure down. Now, this happened in 1980 when we were, when I was actually at that time getting interest into what particular research area that I wanted to embark in that particular situation. So from all this, this line is breaking a picture there. Another one, yeah, this is also, I would say common. Hopefully it is not common. This is actually the normal highway bridge. And you can see that one part of that pillar is breaking up. And this is due to shear. Okay, so this is shear failure. Usually it is 2 separate beams. So the beam actually are just separated out. But the failure is actually on the concrete part that is holding this one. So this is the normal beam, and this is shear. So when we analyze things, we look for shear stress and what is the shear maximum value there. This one is 1999. I can't remember where on the internet. These are from the internet, by the way. Okay, this is shear failure of normal structure. And this one, can you see what is it? It's a pillar. Right. A pillar is holding, supporting something at the top, a certain structure. So it's supposed to be a good pillar like that. And this is what we call strut. Or another term, they call it column. Now see how it can fail if the load is too high. This is not buckling failure. It does not buckle, but it is compression failure. So there's a force from the top in the downward direction, and this fails actually due to compression. You can see all the reinforcement there all jumble up. The load is too high, or the strength of this is weakened by somehow or other. So this is compressive failure of this particular column. Okay. So, okay, the next one, this picture, I remember because this is the time when we were working on NGV, or natural gas vehicle. Now this is a van, I think it happened either in Cheras or in Malacca. I can't quite remember, but what happened is this is a natural gas vehicle. Now, natural gas vehicle should be equipped with high pressure tank, at least type 1, type 2, or type 3. But the owner of this vehicle, he fitted type 1, but legally he fitted the type 1 and got the Puspacom approval. But on his own, he add this tank. Okay, this is household LPG cooking tank, cooking gas. And it is connected to the LPG, to the type 1. So when he fill up his type 1, the type 1 cylinder is able to withstand 200 bar. And this tank will only able to withstand 5 to 10 bar. So when he fill up in the petrol station, as soon as the pressure reaches 10 bar and above, the additional tank that he put in exploded. And that's what happened. Okay. Now, this is the type 1 tank. This is type 1 new. The type 1 tank is still intact, right? And the additional tank is not there. Now, this is circumferential stress, and it explodes because of internal pressure. This is how it looked like. Not very nice, is it? I do not know. I think one person was as a fatality there because he sits in that van during the filling up. So that capacity. Now this is internal pressure, right? Internal pressure failure. Another load which you should not should also take into account is atmospheric pressure. And if you think that atmospheric pressure will not cause failure, then think twice when you see this. Okay, what is this? It is a normal tank, right? Now, I think this happened in one of the European countries. I think I can remember this EYO. It's not a local company, local brand. And cold countries is actually their normal temperature is quite low. So it was, it happened some time ago, I think. And the story is that when this tank stopped, they actually wash it because they want to load another liquid. Wash it with warm water, right? It clean it up and so on. And after that, they close the opening very tight. It is airtight while it is warm inside. Now the temperature outside is about -0 degrees or something like that, or -1, -2. And as soon as the tank cools down, and this is what happened. Now this is the work of atmospheric pressure. Now don't underestimate atmospheric pressure. Okay, that's what I'm trying to stress here. So there are, it happens, some component happen to crash like this as a result of atmospheric pressure. So we take for granted that nothing will happen or nothing will fail because of atmospheric pressure, but think twice. It could happen in this particular case. Okay, another case is this tank, BRPL, something like that. Again, I don't think it is in Malaysia though. Again, it could happen. This is atmospheric pressure crushing. Usually, either it is washed from using warm water and then leave it to cool, and then it is what happened. The internal pressure reduction, and you have the what do you call that, atmospheric pressure. Type of nut failure is the thread extension. Okay, this is a ductile material and it extends. Once it extends, there's a phenomena called Poisson's ratio and there's a reduction in diameter. So it's no use anymore. So this is failure at the bolt. This is failure at the thread. Another type of thread failure is the thread. Okay, so you should relate that. Okay. Okay, this is buckling failure because connecting rod is actually have got axial load in compression. So this is pin joint as far as column analysis is concerned, and this is, it can fail in that manner. Okay, so this is buckling. Okay, so ClO5 related to this. And this is another one, tension failure, and this is a motorcycle chain. So this is a failure due to tension, ClO1. And the pin there could also fail under shear, that's ClO2. Okay, so at the end of the course, you should be able to assess how to prevent this. Okay, so just to close this one up, hopefully it will give you some interest more and give you some motivation to understand.
Okay. Hi there, are you there? So just now we had all the types of failure, structural component of structures, how they fail, and different types of forces and the mode of failure, isn't it? What are the types of failures you learn? Due to compression, due to tension, due to bending, due to torsion, due to shear, right? These are the things you're going to learn in different chapters. We'll do one by one. First we do the stress, then strain, and then relationship between them, then torsion, and so on. We'll do it, right? Now continue with this, our slides. Right. I posted the slides in the CN, please follow, and then the homework also you have to complete it. Let me take the next slide for you. Any question in the video? Any question? No question?
No.
Okay, like this, there are plenty on internet. You can find out the types of failure. Especially, you please mark this this one, big blue crane failure. Is fully explain about the structural failure, what point and why, and how they rectified it. All these things are there in that video. You can see to understand and appreciate this type of learning. Why it's important to learn stress distribution, right? Take the second one. Okay, let me go to the second slide. So once you learn how to analyze this stress, in addition to, so far you learn the forces, now you need to know how to analyze what? Can you? Yes.
Weren't sharing. No, you weren't sharing the screen just now.
Yeah, screen is there. I shared already. Can you see it? Understand?
Yeah.
Yes. Yes. Right. So overall, the summary of what you learned just now from Prof. Bhargavi, all the examples, it's all showing later. Before the video, I showed two things, which is load and the body force. What is the load coming in and how the body respond, right? Overall, what you learn from here, from these types of failure, these three things. Nature of superimposed loads are important. You should understand the nature of load, whether only the live load is there, only the machine load is there. In addition to the live loads, whether atmospheric pressure load is there, atmospheric load is there, gravitational load is there, all these things you have to check. And then Next important factor is the material property and its respective behavior, especially material property is referring to brittleness, ductility, malleability, right? Palatability, all many are there, but these three are very important in checking the material property, compatibility of the material to withstand the overcoming load, right? Mostly they will check for these things. And in our case, we'll have later we'll have a common distribution between stress and strain to know all these types of limits on the loading and its failure. Finally, type of stresses developed in the body due to one, right? Due to this load, what are the types of stresses? If it is tension, tension stress, compression, compression stress, shear, shear stress, and so on. Okay, let's see one by one. Stress calculation, you need to follow this receipt for calculation. Today I will work out one or two questions before the class ends so that we can continue. You can continue working out. Over this weekend, I will post the text for you. I was waiting for all people to be in so that they can receive it. I post the text and the solution material as I promised last time. You can follow for working out the calculations. Right. Coming to the recipe of calculation, determine the external force. First one, you should know what are the types of forces acting for the given situation. It may be a truss, it may be a beam. Just now you saw different types of structures, right? Maybe a shaft, maybe a crane structure, maybe a structural member, or a turbine, or a Pelton wheel, rotating Pelton wheel, or any type of situation, right? Or a load which is supported by at the wall or by a hook. All these examples we will work out. Selectively we will work out. In that, first thing you should know what are the external forces, right? And then calculate. You should know this. Here we ignore the weight of the body, right? Because all designs, all structures, assuming that it is on ground, we will ignore the self weight of the body. But when you go for actual design in RCC, right? In real reinforced concrete structure where you really design and detail it, how many detail the members, detail the reinforcement, that case you will involve the self weight or weight due to gravity. Okay. For now, we are only analyzing, assuming it is constant, right? Each and every component or parcel and particle of the material is subjected to equal weight and it is balanced, assuming that we analyze for rest of the forces, which is external forces, right? Maybe line load, wind load, and then the other types of loads acting on it due to connections, due to support condition, all these things we will analyze. Know how to calculate the volume cylinder? Yeah, just basic understanding is necessary. You should know area, surface area of these geometries, cylinders, sphere, cone, prism, and so on. I will provide you then and then, but you should also recall your school. At school, you studied all these things, right? Surface area, cross-sectional area, because we have different shapes and geometries we will be studying. Determine internal forces by cutting section of component requires skills in sketching. Yeah. First one, you determine the forces and reaction. With that, you should be able to draw the free body diagram, not to scale. There are some spelling mistake later, I correct it. Determine stresses once internal forces are determined. Right. External forces, and there will be internal force. According to Newton's law of motion, whenever there is a action, there will be a reaction. Action is by the external load, reaction by the body force. Okay. Whenever the body is subjected to load, it will create an internal force, response of the body, and the corresponding force over area is called stresses produced by the body. We'll study all these things. So you have to calculate. This is a simple step that you have to understand and follow for finding stress produced by the body or stress concentration at a given point. First, know the force, draw the free body diagram, and then calculate the maximum. It may be maximum or average, depends on the question. If it is maximum, you really have to determine the point at which it is subjected to a maximum force. And then the force over area will give you the load over area will give you the stress. Right. And so what are the types of equation we'll be using? Number one, if it is a member with forces and different types of loading, you can use first one, equilibrium condition. Next one is the compatibility conditions. Last one, material constitutive equations. Okay, mostly we will do we will come across all these things over the chapters. I don't spend much time on this, but the tools that you can use for solving problems in stress analysis are: first one, equilibrium condition, and then compatibility equation, material constitutive equation. We will see one by one in detail in each chapter. Okay. Start with, you have to know these four types of four elements of analysis. Most of the question you can find this word: normal force, shear force, torsion, and bending moment. And if these four are forming four different chapters itself, I tell you later, I will explain you later how they are. You see the body here, take this body, consider this body. You can see the directions of loading and the reaction of the body. This one, the one which is acting perpendicular to the surface, right? The one which is acting perpendicular to the surface is called normal. The one which is lying on the surface is called shear force. Okay, for now just understand this. Every day I will talk about this only. So you must come to familiarize with this term. Just understand every day what I say and show the diagram. If you have question, please stop me to ask, clarify, and then in due course of time, I'm sure you will get familiarized with this term. I repeat, a normal force, whenever the body is subjected to any loading, it will create a normal force that is perpendicular to the surface. Another one will be a shear force, which is on the surface or parallel to the area, parallel to the surface area, right? If the body is overturned like this, then you have to say the other way, right? Sometimes it may be a bending, right? It's not a movement. Movement is called bending. Movement really get displaced, get broken, brittle. And then torsion, the body gets rotated about an axis. Okay. Moment is not just a moment, it is very important. The moment is about an axis. Okay. Moment is about an axis in the same plane. And then torsion is also acting. It's a kind of a rotation, right? It's a kind of a rotation. Rotation is a type of failure in some activities, some objects, but in the same thing is maybe operation, any facility which is having the turbine wheels. Turbine wheels is a very good example. The shaft is always in rotation, right? In producing the hydropower or whatever the type of power you are generating. It may be a windmill, it may be a hydropower generation turbine. In all, the shaft is in rotation, right, for a prolonged time, right? The main objective is this should be in rotation and working in good working condition, right? No time it cannot fail. So you determine the number of rotation, the power supply, the material, everything. If everything is perfect, the system is working well. So I mean to say the torsion is not always, the rotation is not always not a failure. Some object, if it is to be stable, if you start rotating, then it is a failure. For example, the high-rise building, right? High-rise building due to earthwork load, sudden earthwork, or sudden seismic load changes, wind load changes, it will start rotating. Then it is called a rotation, where it is to be, where it is supposed to be the stable and equilibrium condition, right? The meaning of normal force, I already explained. It is the force acting perpendicular to the cross-section area or a surface area. If you turn this side, it may be a cross-section area. If you cut and want to analyze at this point, it will be a cross-section area. And the shear force, parallel or lying on the surface itself. Torsion effect is developed when the external load tend to twist or rotate the segment of the body, right? Twist or tend to rotate the segment of the body with respect to the other about a perpendicular axis. About a perpendicular axis, that is important. Rotation is about a perpendicular axis. Bending moment, as I said before, it is a moment acting about an axis. That's important. It's always about an axis lying within the plane. Right? Later, when you do calculations, you remember this point. This again, you can go through like just simple one only. I already explained. Let us do this small mathematics. I quickly finish this and go to one calculation at least today. Can you see this? Let us take and understand how this cross-sectional area is contributing to the stress distribution or otherwise the stress concentration in any structural member. Take structural member, take a beam, which is very common and the one you can understand. Take this beam with a cross-section 4 by 4, length is 10 meter, right? The stress is defined as pressure over area, okay, or force over area. Stress is defined as load over area or force over area. What is the unit of stress? What's the unit of stress? Unit of stress, please. 25, 3 absent. Last class all present, this class 3 absent. What's the unit of force? I mean the stress, quickly. Last class I explained the very basics one. This is Newton's, right? Newton over?
Newton over meter square.
Yes, Newton over meter square. 1 Newton over meter square is called 1 Pascal, right? If it is 10 power 6, 10 power 3, accordingly you can change it to kilonewtons or kilopascal or what do you call megapascal. Solids use mega, liquids use million if it is 6, okay? Right, let's take this object and then find out at any cross section if you find out, imagine there is a 5 Newton acting at the ends, okay? You're pulling this member by means of 5 Newtons at the ends. What happens at any cross section or at this point or this point, if you calculate the stress, it will be pressure over area, which is just 5, cross section is 4 by 4 already given. You end up with how much value?
0.31.
Very fractional value, pascals are exerted by the body, right? The stress is the response of the body or the reaction of the body. Now, okay, what happens? What happened actually? It is the quantity law that everyone can do it, every engineer do it. But really you have to understand what is happening. When the body is pulled by certain P in newtons or kilonewtons, automatically the material property will tend to respond in the opposite direction in this way. Okay, please understand this point. Action and reaction. Because of the material property, it will tend to react, pull back the material to the original position, right? Or respond to this body like this. And then due to this one, if there is nothing, it will stop here. Because there is another load acting in this direction, the material in this area will tend to act in the opposite direction in this way. Come on, next scenario. When you cut and take out the section, you may see like this. This is called body response or stress generated by the body due to its inertia, due to its material property. It may be brittleness, malleability, or palatability, or ductility, right? Whatever the strength it has, due to that, it can respond, try to restore the body to the original condition because it is going to negging, right? When you pull long, it started negging. Negging means thinner, the cross section will be getting reduced. You keep on pulling. But what the member does, it will try to regain its original size by pulling inward or in opposite direction like this. At this condition, there is another one. Okay, come on, let's go to the next scenario. Once it's pulled, a negging means thinner the dimension due to this pulling outward, the cross section will tend to thinner to the extent of 1 by 1, say 1 by 1. Initially it was 4 by 4, isn't it? Initially it was 4 by 4. Now it is 1 by 1. Change to 1 by 1. See here the cross section. The cross section, the cutting section at BB, cutting section at B. There's a diagram, cutting section at BB, having cross section 1 by 1 instead of 4 by 4. Now calculate the stress at this cross section. If we calculate it, force over area, same force over area 1 by 1, end up with 5 Newton over meter square. Do you understand this? So see the other hand, case 1 where the cross section is 4 by 5, you end up with 0.31. On the other hand, When it is pulled and the cross section changes, cross section reduce, the value of stress change to very high, isn't it? Now you understand the effect due to cross section. As the cross section decrease, the stress distribution will be intense, very high, isn't it? Having understood this one, right? Having understood this one, you should try to avoid thinning effect. I mean the negging effect. You should design the cross section in such a way that you will have proper distribution of the stress, proper distribution of stress produced. You have to design by this one, not this one. If you have this section, automatically the stress production will be very high. After some duration of time, it will tend to bend or break or bed compress according to the type of loading. If it is this per meter square, the distribution is only 0.31, right, and spread over 4x4 area. So this is explaining the variation due to cross section. Let's do this calculation. All of you write down, take your notebook, all of you switch on your camera quickly. I'm going to work out this in my notepad, then you can follow. All of you write down this question in your notebook. Can you write down this question in the paper? I told you, switch on your camera please. I want to take snap. All of you switch on your camera. See, you are not coming to the university. We are not meeting in person. The internet is good in the university where I'm working. Don't worry. You please try to keep on your camera. Keep the notepad, the papers, working sheets with you, calculator. That is how you have to practice this paper. Otherwise, you will get bored very soon. All of you switch on your camera, keep the calculator on top, and then keep the paper, write down the question. Good, thanks, Ward, Tian Supai, Pagi, Khairan. Write down the question or write the given data only. Write the given data, and then the drawing you don't have to do. The slides are there. Just write the given data or the question only. I'm going to solve now. Come on, quickly. I take a snap and then go to work out the question. We are going to now do the stress calculation, a small example wherein you can understand the method of calculation. Get a print screen. Okay. Let me work out this question. Please follow the instruction clearly. If you don't understand, ask me immediately. Okay, let me take 1 minute to turn to notepad. Very simple question, the calculation of stress. I use my tablet mode. Okay. Can you see the screen? One moment, let me share. Okay, can you see? Right, let's solve this question. What is given to you? One of you read the question, please. One of you read the question. Can you hear me? Okay. Can you hear me? You are given with a bar, right? There is a bar with different connections, right? It has a different connections. has a constant width of 35. Can you hear me? 35 mm and the thickness is 10 mm. You can hear me, right? Okay. Means cross section is given. You are given with the bar supported. It may be supported when it say the ends. It seems it is supported or just hold by the certain type of loading at the ends. The cross section is 35 by 10 mm. Determine the maximum average normal stress in the bar when it is subjected to a loading. Okay, number one, you should understand the principle of the mechanism of structure. Whenever it is subjected to a loading, for example, last time in engineering mechanics, you used to have a member, beam member like this, maybe support in the simply supported condition, a load of P is acting, right? It will immediately tend to bend, right? It will immediately tend to bend, and then you calculated the corresponding shear force and bending moment, right? Shear force and bending moment, don't forget, these two are the very important thing engineers have to know and design. When you take the shear force, it is across the, if you take the cross section and cut section may be like a rectangle one, across the cross section, right? Shear force will be acting across the cross section like this. On the other hand, bending moment will be tend to bend, maybe in the clockwise direction or anti-clockwise like the direction, it will try to bend. So you found out what is the shear force acting, what is the bending moment acting, right? These two type. Later you will study how this bending moment is, whether it's a compression or tension. All these things you will learn later on. But this part you already studied in your engineering dynamics, correct? Now coming to right. Now let's take our case of the problem, example 1, right? Example 1. What is given to you? Here the case is different. So far you learn what is shear force and what is bending moment in the axial direction or in the vertical direction, right? Along the cross section, how it was acting. Now it is across, which is called normal. Okay, first write the given data. I assume that you already written the question. Okay, write the given data. Please follow the strategy and 4 strategies that I have given before in solving in our first class. So the given data cross, it's a bar, right? It's a bar supported at the end. Cross section area is given. Let's find the area. You can find the area here itself. 35 mm by. Better write with units, otherwise you will have problem. What is the answer in meters? What is the area in meters? If we can change to meters, 3035 meters times, it's a rectangular, it's already given width and the depth, so it is a rectangular. Area of the rectangle will be like this in meters. So I end up with how much is the answer? Area in meter square, please work out. Everyone work out. The next data given to you is, if you want, you can write the bar also. The continuous bar is given to you. Come on. What is the answer, please? That's all the given. The loads are given, right? The loads are given. The next data is, what's the answer? Work out and tell me. I will ask anybody. Loads are given in the diagram. The next data given is in the diagram. I can copy and paste the diagram here, or otherwise for now I just draw it myself, a simple sketch. Later we'll do it, and then required answer will be, required solution or required answer is to find what is the maximum normal stress. You have to forget for a while all that shear force and bending moment that you have solved before. It is totally a different case. We are going to solve for the stress distribution across the member, right, across the cross section due to normal stress, right? Maximum average normal stress, very important, normal stress. This one is new to you in this syllabus. First of all, understand where is the location of this moment. This is the required answer, right? Now solution will be like this. Solution. Do it. Right. What is the answer for area? Anyone? Area, please. Nobody getting it. Can you answer me? Anyone?
0.00035.
Correct. Any? Please check. Oh, it's 0 1 only. Right. Correct. 2 times. Okay. Good. Then here solution is. Come on. Let's draw the free body diagram. I have written the given data. Better you draw the free body diagrams. Then easy for you to know where is the location of the maximum load, because you're asked to find the maximum shear of average normal stress, or maximum, should not be average, very bad term, maximum normal stress. Okay, and let it be maximum normal stress. Why they say average? There are many arrows inside and they take the average, right? Free body diagram. Let's start with free body diagram. Reduce this thickness and bad writing. Okay, free body diagram. How do you do? Start with, take the different section. You cannot, in the question it is given A, B, C, right? Can you see in A, B, C? Have you taken the question over there? Wait, I copy and paste here. Better. I copy and paste the structure here. I think I can copy and paste. Let me check. Okay, copy. Okay, good. Come on. We are doing this structure member. Where do I cut? Right. This is our. Okay, try to understand this. We need to do section by section to understand the loads given and the corresponding stress produced. Okay, you are given with, can you see the, this is also problematic one. Can you see the arrow moving on the screen? Okay, you can see, I think. You can see, right? Yeah, you can see that. Right. It's better you analyze by the part by part. You are given with A, B, B, C, C, D, right? And this is supported by a 12 kilonewton load acting on it. There is a support which is acting at 12 kilonewton here, 20 kilonewton at the other end or towards D, right? Let's understand section by section so that you're asked to find maximum, right? Let's find where the maximum load is so that you can calculate for maximum stress. Come on, let's take the AB, section AB, number 1, section AB. I solve for the section AB first. So section AB will be having, I just draw a straight line, which is AB, right? AB, and this is the point, right? You have how much here in this direction? 12 kilonewton, right? 12 kilonewton. 12 kilonewton. Let's write it down. And then what is acting in this direction? Just take AB only, right? When there is a 12 kilonewton acting on it, automatically there will be a equal and opposite load acting equal to 12 kilonewton. Agreed with this? I taken the AB section only. When there is a load acting on it about 12 kilonewton, immediately the member will respond in opposite direction, right? From this point onwards, if you check 12, 12, 12, 12 until this point, until there is another type of load which is 9 kilonewton coming in, right? Just before 9 or before this point, can you see my arrow moving? Just before B, until just before B, it will be acted upon by 12 kilonewton. When it crosses with 9, automatically, depending on the arrow direction of the load, it will change. For now, just keep it like this. So the value will be PAB until AB, means in before B equal to 12 kilonewton, right? Keep it like that. And then we are now analyzing only. Later we will find the most vulnerable point. Let's take the next section. Next section from here is B to C, right? B to C. I just proceed with this one, or I have to draw it again once again. A pin, right? And then it's supported by another disc, and then followed by another one. So what's happening here? There is a 12 acting on it, 12 kilonewton acting on it. So corresponding load is produced already, and then now acted upon by additional 9 kilonewton on top and bottom. 9 kilonewton on top and bottom. Are you following? 9 kilonewton top and bottom. So how much is the total load acting in this direction? It will be 12 plus 9 plus 9, which is 30 in this direction. Automatically this member will respond, or from this point onwards, hope you can see my arrow moving. See my arrow moving. Automatically from this point onwards, this point onwards, I remove this arrow. Automatically from this point onwards, it will change to, the member will act in the opposite direction, equal and opposite to 30. So it will react in the opposite direction. So total load acting in this direction is P due to external load. So the member will respond equal and opposite, which is 30 kilonewton in this direction. Moving on, next section. Are you following, everyone? Then followed by next section, which is CD. Let's check, or I just write down here itself. When you check from CD, I just mark here. CD, there's a disc, and then proceed our ring, right? A ring, and then a support. How much is again? 22. This is 22, right? 22. All right. And then what will happen? Due to 22, there will be an opposite. Until this point, it was 30, right? It was 30. After this is here. I show you here. Until this point, please follow my arrow. Until this point, it was 30, isn't it? Automatically, there is an opposite. We have calculated 30 in this direction, right? 30 in this direction here. And then there is an opposite load which will reduce the 30 value to 30 minus 4. It will be 26. And moving on, there is another load which is acting in this direction due to 22, will be another opposite direction, it is 22. So it will reach the 22 load towards the end, and all these things are lesser than this 30, isn't it? From C until N, it is going to be lesser than 30. Hence, we decide the maximum load, we can come out with the answer, the maximum load or force acting on it, acting on this bar is equal to 30 kilonewton. This is one answer. A direction also you can put. Okay. Now stress. Hence you can calculate the stress. We got the maximum load by analyzing the member from A to C, A to D. We can calculate the most highest stress value which is acting on the member, or max, sigma max equal to P max divided by the area of cross section at that point. Okay, if the area of cross section is changing, you have to do. But we found the 30 is acting at this point, isn't it? Acting at this point, So cross section is 35 by 1. Already we found out the area. So we can calculate the area's load is 30 kilonewton over area is here. Is area this one 30 point area, better I use the thick one. There's a 00035, 00035 area we already calculated, 00035 meter square. So what is the answer, please? And this one you change to newtons, okay. What is the answer? Anyone? Anyone? Are you there? Just we're going to finish. Sorry, I took 3 minutes late. What's the answer? In we are having newtons, right? Newton over meter square, please. You're going to end the session, please. You may have to solve the rest of the questions that was there in your homework. Come on. What's the answer here? Are you following?
85714
85
714
714
285.
Give me the points. 2
85
85 then
0.71
megapascal. I just write down from the answer. Are you getting this answer? You will get in Newton meter square, which is Pascal, right? 1 Pascal. Again, in terms of Pascal, you can write down ROE. Later, you change to into 10 power 6. Later, you change to 10 power 6. Remove the 10 power 6, you put megapascal. You will end up with Newton meter square or pascals. Okay, or pascals. Later, you change to megapascal. This answer. Are you getting this answer? So now we got the maximum normal shear stress, which is acting at that point. The shear stress which is acting in this direction, right? The load is in this direction, is follow the stress in this direction. At which point? At C or before C, the value you can take it as a BC. Between BC, the force is acting and the stress distribution is this much, 85.71 megapascals. I end here for the class. Any question you can ask me? Are you clear with this? Are you following? Any question, critical question that you don't understand? We have to analyze the member part by part to identify where the maximum load is existing. If you plot and see, it will be interesting. Wait, I show you the plot. Actually, I wanted to explain the plot, but time up already. Maybe next class I go. See here, it's already there. You can see. Wait, I'll share the slide. One more, last minute, last 1 minute. See, in the loading also we can explain about how this is. See, the diagram started with 12 at A and then gradually increasing, maintain. When 4 is coming, it is getting reduced and then reaching 22 at the other end. So overall the member is maintained equilibrium condition. This plot I will explain next class if you want, or one by one. But now we found the value of maximum normal stress acting in this member at this point to be 85.7 megapascal. Any question? I stop here. It's a very simple question, one line answer for you to understand how to calculate the stress. Stress is load over area. I share this tutorial sheet for you in the CN, the one I have worked out. I will share it in the CN. You can take it. Similarly, you work many questions. Maybe I spend an hour, 1 hour I do theory, 1 hour I do this type of calculations every week. With that, you must get familiarized with the calculations. Any question? If no, you can leave the class. I stop recording.
Excuse me, doctor.
Yes.
I have a clash on class of today with another subject. Is it
What
possible
subject
to
is it?
change the